Okay, so as you noticed, the content of this module is divided into two parts, which are divided as two chapters, and there's chapter 7 and chapter 8, and here we have algebraic structure, and here we have vector spaces. Okay? So let us start looking into algebraic structures, and let us look at some basic concept which I expect you to remember. And the first basic concept is, what is a group? So if I ask you to say what is a group, would you be able to give an answer? So if not, what is it? It's an algebraic structure where every element is invertible, which means that there exists another element which you call g minus 1, such that g dot g minus 1 is equal to e. Of course, this definition here is hiding the definition of monoid, is assuming that it is also monoid because I'm talking about mutual elements, and it's of course also an algebraic structure. Okay, it does not show here the associativity, but it's also associative. And if I then ask you, do you remember what is a subgroup? Okay, what is a subgroup? It's essentially yet a group, but where H is a subset of G. And still, this is a group, which means that this property is still valid. Now, do you remember what is a coset? Do you? Or do you remember how to build a coset, at least operationally? You need to pick up, let's use a different color. You need to pick up one element G from G, and then you need to consider all the elements of H. And then you apply, so H, let's imagine, is a set that is like H1, H2, and so on, Hn, whatever. And then to build up Hg, blue, what you need to do is, so Hg is a set, is not an algebraic structure, of the type built up as H1.g, H2.g, Hn.g. Do you remember it now? Right? And do you remember that it can be right or left, but we have looked into commutative cases, so for you the two things are the same, because Hg is equal to Gh. Now, starting from this, there was a lemma, which we have seen, I think it was lemma 3 or whatever. And it says that the cardinality of H is equal to the cardinality of Hg. Do you remember how to prove this? Any idea? Would you like to try and challenge yourself for the next 2 minutes to try to remember what you have to do logically, and then I show you step by step. Okay? Shall I stop the shall I stop recording for this 2 minutes? Okay? And I'm going to give you a hint to help you, and the hint is build a bijective function. Okay? Try to see if this helps. Let's stop again. So, the proof of this is obtained by building up a bijective function, which we are going to call phi, or phi, which goes from H to Hg. Okay? And so how does this work? Just to understand. I can count the elements of this set, and the elements of this set, I can say that the number is the same, so that they have the same cardinality, if I can build up a one-to-one relation, or if I can build up a bijective function. We have talked about that. And how does this work? It means that I have to find a function which is at the same time injective and surjective. In order to check that it is injective, I have to pick up two elements, h1 and h2, and they must be not the same. And then I need to verify that phi of h1 is different to phi of h2. Let us write it this way. I put different, and then I put a question mark. How can I verify it? Simply phi of h1 is equal to h1 dot g. Phi of h2 is equal to h2 dot g. And I know that h1 is different to h2, and therefore I can actually say that h1 dot g is different to h2 dot g, which is the first bit of the proof. Okay? I put this up. Of course, you need to know what injective is, otherwise you can't really answer to this question. And now, you need to know what surjective is. Surjective means that all the points in the codomain are mapped by points in the domain. So, if you remember, last year we were saying things the type f is a function, it goes from a to b, then what were we saying to say that this was surjective? We're saying that it is surjective if for all y belonging to b, there exists at least an x belonging to a, such that y is equal to f of x. Or, if you like, x, y belongs to the function. Right? What does this mean in terms of phi in this case? It means that if I consider a certain y, but now my b is hg, which belongs to hg, this means that y is equal to a certain h, which I don't know which one is, by g, which is the only one that I've taken. Okay? Because I'm taking only one element from the group and all the other elements from h. So if this one belongs to this set, it means that there exists an h such that this is verified. And since there exists an h, because I can write this, therefore, phi is surjective. Come on, we have seen this in detail, so I cannot go too much again into this, but okay, do you remember it now? Do you see it? Okay? Of course, you must know what surjective is and what injective is. Otherwise, essentially, you are not able to count numbers. And just to let you know, the bijection is what, if you remember the example of last year that I was saying that, for example, enumeration is means establishing a bijective function between two sets, and it is somehow means that I have this ones and I say 1, 2, 3, and so on. That's what I'm doing is a bijection. Why is it a bijection? Because as long as here I am taking a different number of markers, I have now here a different figure on my other hand. Okay? And that means injective. And surjective means that every time I do something like this, there is something which corresponds in this other hand. Okay? Fine. Okay. Having said this, we move to the next question. And it is, would you remember what does the Lagrange theorem says?
Isn't it the cardinality of G over the cardinality of H equals K?
Yeah.
Cardinality of G, cardinality
H
of H
equals G.
As
K.
Where K is
Belongs
what?
to N.
Yeah?
And it's not 0. Is that
yeah, well, it is empty, but yes. So, would you be able to prove this?
Yeah.
You would. Before we enter into the proof, you need, in order to prove this theorem, 3 lemmas. One is what we have just proved, and it is that cardinality of H is equal to the cardinality of HG. What are the other two lemmas that we need? The union,
Yeah, so like G equals to, yeah, so N,
G equal to,
then N on top of the union,
yeah,
I equal to 1,
okay.
HGI.
By what? GI?
HGI.
HGI, like this. Okay? And the other one?
Isn't that something to do with it being disjointed?
Yeah, that's for all, that every two cosets, they are disjoint. Okay? So, yeah, that's correct. So that, yeah, if I take any pair of cosets, they are disjoint. And that was opening there was another story about that you might remember, about congruence relation. Do you remember that I was talking about congruence relation? I hope so. Yeah, of course, and in order to prove that part, you need to know what an equivalence relation is. But let's not get there. Let us simply take 2 minutes and please try to prove the Lagrange theorem while I pause the video. So, the proof of this theorem comes from these 3 lemmas. So these are the 2 ones. And the other one is that for all I, and if I take HG I, I'd say for all I and j, HGI and j, and HG intersection HGJ is equal to the null set. So they are disjoint, unless for I different to j. So which means that 2 cosets either coincide or are disjoint. Okay? So, in order to prove this, what we have to do is is to start from the consideration that G is the union over I equal 1 until n of H, G, I. But since they are disjoint, so HGI, so what does this mean? This means HG1 union HG2 union HG3 blah 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 union HGN. Okay, you understand up to here? Now I have to calculate the cardinality of G. So which means is, okay, this set is the union of the set. Okay, how many elements are in here? Since they are all disjoint, so yeah, you understand disjoint. It means that the cardinality of this one is nothing else but the cardinality of HG1 plus the cardinality of HG2 plus the cardinality of HGN. Right? But each of these cardinality is equal to the cardinality of H, which simply means that this is a H plus H plus H plus H, which means, well, I used K over there, but it doesn't matter. Let's say N is equal to N times the cardinality of H, which follows that the cardinality of G divided by the cardinality of H is a natural number, which is a proof. Okay? Come on, this is not difficult. I am skipping examples, but I mean, please look at them, because you need to understand what they are. I mean, we have seen only 2 examples about this. Do you remember? Do you remember us seeing 2 examples? One was about a cyclic sum, and the other one was about Z5, or multiples of Z. Okay, so having said this, let us slightly change the topic. And still talking about groups. If I tell you, do you remember what means that a group is abelian? It means it's commutative, nothing else. So it means that commutativity is valid inside the group. And the proposition I'm going to ask you now to prove is nothing difficult. It says that if I consider a certain group G dot, we say that this is that if for all G we have belonging to G is equal to G minus 1, so if every element is equal to its inverse, it follows that G dot is abelian. Do you remember how to prove this? I'm going to give you a hint, and then I'm going to give you 2 minutes again. Abelian means that for all H and G, HG is equal to GH. Yeah? That means commutativity. So, now, what I'm asking you to do, let us see if I start it for you, is to start from HG and say that this is equal to H minus 1, G minus 1, right? And to continue. So now, you continue from this point on. Okay? Okay, so by using that one, we have that this one is equal to G, H, all minus 1, which is equal to GH. Proved. That was it. Okay? Now, we have to quickly, sorry, move to vector spaces. Leave this up. Of course, I've also shown you the proof of the one written in red. Please, you must know that as well. Well, I mean, you must know those 69 pages in total. Okay, next. A vector space. So, let us make a little bit of recap. So, we have seen what is a vector space, and in order to have a vector space, we need a set, we need the 2 operators. One is internal composition law, one is external composition law, and we need that 10 axioms are verified. And but 2 of those axioms are really important, and are the axioms about the closure of the set with respect to the 2 operators. And this is defined over a field, which is essentially a scalar field of R. Well, R plus and dot, where actually R plus and dot is not the same plus and dot, but you know what I'm talking about. So this is a field. And next, I've shown you that if I take 2 vector spaces, U and V, then we know that U intersection V plus and dot is also a vector space, right? And we have also seen that S plus and dot is a vector space, where S is what? Is the sum of U plus V. Now, I am giving for granted that you know what the intersection of 2 sets is, because we really have to move on, while I'm not giving for granted that you remember this. Okay? So I'm going to remind you what means S U plus V, and I'm going to do it in 2 different ways. So one way is that S is a set of all those W belonging to a general vector space E, such that there exists, such that there exists an element U belonging to U, and there exists a certain element V belonging to V, such that W is equal to U plus V. And if you do not understand it in this form, you might think that S is the set of all the possible combinations of two elements of U and V. Or, if you want to see through a Venn diagram, this is U and this is V. These are 2 sets, okay? And inside here I have U1, U2, and here I have V1, V2, right? And they are all vectors. Here, I'm having S. Inside S, I have W1, W2, and so on. What is this W1? Is the sum of 2 of these. I don't know which ones, and it's the sum of at least 2 of these, meaning that I can also combine that by adding up 2 others. Okay? So that's the sum. And then we have seen plenty of examples, like, for example, if I consider a set that is an horizontal axis and a set that is a vertical axis, then the sum of those 2 is a plane. Do you remember this? I hope you do. Do you know what I'm talking about? Yes. Great. And now we move to a slightly different topic. And the slightly different topic is the direct sum. So the direct sum, let's still indicate with S because it doesn't matter, but we indicate with this symbol here, is what? Is the sum when U intersection V is what? Is only the null vector. Okay? Then we have seen a theorem which was slightly more interesting than the others, which was saying that S is a direct sum if and only if, which means that the U intersection V is equal to the null vector, if and only if there exists only one element U belonging to U, and there exists only one element V belonging to V, such that W is equal to U plus V. Okay? Do you remember this? Which means in that diagram, let's move this up, and this up. And actually, I've even included some graphics on the notes, on the book. So you can find this drawing also on the book. I'll take a different color. This, if I'm talking about direct sum, it means that each of them here corresponds only to 2. Okay? Over there. So, or if you like, there is a bijection between the elements of this set and pairs of these two sets. Of actually a Cartesian product of these two, but it doesn't matter. Okay. Right? Do you follow? Fine. Do you remember how to prove that? Do you? Give it a go. Okay, the proof of this is made up of 2 parts. So the first part is, let's say, this way of the proof. The second part is this other way of the proof. So we start with the first part and say that if U intersection V is equal to the null vector only, then by contradiction, so it is done by contradiction, I say what? That there exists U1 and U2, and there exists V1 and V2, such that W is equal to U1 plus V1, and W is equal to U2 plus V2. Do you understand the structure? So I'm saying that, well, I cancel that, that instead of having only 2 lines, I've got 4. Okay? So, and if this is the case, I can subtract, I can, let's say, this equation from this equation, which means that this leads to say that the null vector is equal to U1 minus U2 plus V1 minus V2. Clear up to now? Then what do? I simply rearrange this and I rewrite it as U1 minus U2 equal to minus V1 minus V2. Okay? What do I do now? I start considering where do these vectors belong. So to what set do they belong? Okay, you got me. So this one is definitely belonging to U, because it's just the subtraction of 2 vectors belonging to U. And this, for the same reason, definitely belongs to V. But they are the same vector. Since these 2 vectors are the same, this also must belong to V. And this also must belong to U. Which means that this one belongs to the intersection, and also this one belongs to the intersection. Okay? And if this is the case, and I know that the intersection there is only the null vector, then I know that this one, that is an element of the intersection, is equal to the null vector. Because that's all I have in there. U1 minus U2. And here I have V1 minus U2. Okay? So, and this means that U1 is equal to U2, and that V1 is equal to V2, which is the first part of the proof. So, and that, which means to say that if I draw 2 different lines, when I actually check, they are the same. And we have done plenty of exercise. So I'm trying to refresh the theory, but I would anticipate that if I give you 2 vector spaces, then you are able to say you're able to think about an example when this is happening, which is so this means, for example, two crossing lines, or when the solution of the system of linear equation is only 0, 0, 0. Okay? Are you with me? Well, I hope. Now, the second part of the proof. The second part of the proof says that if there exists only one, and so on, if that statement, then it follows that U intersection V is equal to the null vector. Okay? How do I prove this? By contradiction, I make this statement. I say that there exists a certain vector T, which is not the null vector, and T belongs to the intersection. Okay? And then this part is trivial, because it requires just to say that I know that the U intersection V plus and dot is a vector space. Then I need to know the axioms, which means that minus T belongs to U intersection V. Then I can write that T plus minus T is equal to the null vector. And then I make a different consideration and say, but hey, this is the null vector, therefore I can rewrite the null vector as null vector plus null vector equal to null vector. So I have written one element of the sum, well, as in two different ways. Therefore, I reach the contradiction. Okay? Fine. Now, let us move. We are a bit short of time, and there is a few things that I want to tell you, because I don't see you anymore until both the dates of the phase test. So, let me be patient with me a bit now, but hopefully this is going to be helpful for you to successfully pass, get a good grade, and so on. But of course, yes, you must revise, you must study. You will not be allowed to have any note or anything at all, no calculator during the phase test. Now, the next. Do you remember what is the span of a vector space? What is it? It's a set, to start with. So if I consider a certain vector space U plus a dot, and I consider V1, V2, Vn, and vectors belonging to U in this case, and I write L of V1, V2, Vn, what do I mean? Yes?
All the possible linear combinations.
That's correct. Which means this. Lambda 1 V1 plus lambda 2 V2 plus lambda n Vn. And this, maybe this is not very friendly, but I mean, you are mathematicians now. This should become friendly. This means that these values are fixed because they are just n vectors. And these are infinite numbers that can be multiplied by each vector. Okay? And then which means essentially what Chloe was mentioning, all the possible linear combinations. So that's a span. And what is a basis? What is the basis of a vector space? Do you remember?
Linear combination that...
One second. A basis is, we need a noun, is a set of vectors.
Yeah.
Okay? So, basis, indicated for example W1, W2, Wn, is a set of vectors. And these vectors have got two properties. What's the first one? It is what you were saying.
They span the vector space. Yeah.
So lambda, L of W1, W2, and Wn. So they span the space, for example. Yeah? We are now referring to this vector space, doesn't it? And the second property is what? Correct. Well done. W1, W2, and Wn are linearly independent. Okay? Let us now, the order of a basis is the number of vectors that belong to a basis. Okay? Let us prove proposition, all the bases of a vector space are of the same order. Before you start thinking about this, you need to remember one very important theorem of this module, and which is called Steinitz lemma. What does it say?
That S is less than or equal to N.
Okay, yeah, well, what is S and what is N? So S is less or equal to 12. Okay. What is S?
The number of vectors in the basis.
Not quite. This is the number of linearly independent vectors.
Oh, yeah.
And this is what?
Number of vectors spanning.
Correct. Well done. Number of vectors spanning E, let's say. Yeah? So this is the Steinitz lemma, which can also be stated that the number of vectors that are linearly independent cannot overcome the number of vectors spanning the vector space. You are going to need this, so that's why it's a lemma, in order to prove this. Any idea how to prove that? Think 2 minutes, and then you show me. Okay, so we have got two bases. One is V1, U1, U2, Un. V2 is V1, V2, Vs. But a basis is what? It means that we have n linearly independent vectors and n vectors that are spanning E. And here we have S linearly independent vectors, and we have S vectors spanning E. So I write this here. So n vectors are spanning E, and n vectors are linearly independent. And here I say S vectors are spanning E, and S vectors are linearly independent. Okay? I'll just written a definition. And I know that the number of vectors that are linearly independent is less or equal than the number of vectors that span E. These two things together means that that n is less or equal than S. These other two things together, S vectors are linearly independent and n vectors span E, together mean that S is less or equal than n. But if this is less or equal than this, and this is less or equal than this, it follows that n and S are the same thing. And they all have the same basis. Come on, is this difficult? No, it's fine.
You didn't show it like that.
How do you show it?
So it's, I mean, it's the same sort of thing, obviously, but it's just.
Logically, it should be the same.
Yeah.
I mean, well, maybe I have graphically written in a slightly different way. I've been more improvising to prove it. It should be fine. Okay. And now let us address the beast. Or maybe I can give you a break, but I ask the question first. Have you seen the Grassmann relation? Okay. What does it say? Have you seen that? You should have seen that for a full hour. Like 1 hour, one proof.
Yeah.
It's a big one, but actually my advice is when you study, okay, of course you read, then you close the book or close whatever, and you start writing on your own paper. And then you check it, and then you restart writing again. When you have written like 3 times, you've learned it, and ideally you are able then to continue on your own, to rewrite it on your own. And then you see that it's not that much. You should be, every time you do it, you should be a bit faster. And eventually, to write down that takes, when you know where you're going, it should take like 6-7 minutes, maybe maximum 10, to write it down. And so at first, what does the Grassmann relation say? I've got u plus and dot, v plus and dot. The dimension of u plus the dimension of v is equal to what?
Dimension.
It's equal to the dimension of S, which is the of u plus v, plus the dimension of u intersection v. Or this can be also expressed as the dimension of u plus v, of course, is equal to the it's the same, to the dimension of u plus the dimension of v plus the dimension of the intersection. Okay, I'm gonna give you a bit of break now. Okay, so the proof of the Grassmann relation is built up in the following way. You need to state a certain basis of u, which you write like u1, u2, ur, then bv, a base of v, which is v1, v2, vs. Essentially, you are saying that the dimension of u is r, and the dimension of v is s. Then you state that the dimension of u intersection v is l, and it is and the basis is t1, t2, tl. Up to here is fine. Then, since these elements are common to u and v, you can use them inside the basis of u. So you can replace some of the vectors for several theorems that you have seen. Some of the vectors from this basis with these vectors here. So you can rewrite the u in this way, like t1, t2, tl, and then you put the other ones from what you have. u, l1 until you are, and you do the same here. Okay? Do you remember it? I mean, you should see it, you should have the video, you should have it written in several forms. Okay? And so you say that these are two bases, and then you say, I consider a certain vector w, which belongs to S, which belongs to the sum of u plus v. How can I build it up? I build it up as a linear combination of the elements of this basis and the elements of this other basis. And I start adding them up like this, and I find out, but it's pretty obvious, that these elements are actually having the same, so that this element here and this element here have got the same vector. Therefore, I can group them in this way. And this means that I'm spanning, so the state of the first part of the proof ends here, saying that I can span S equal to u plus v with r plus s minus l vectors. This is the first part of the proof. Then the second part of the proof consists of taking these very same vectors, multiply them by some coefficients, and impose that that one is equal to the null vector. Essentially, I'm checking whether or not they are linearly independent. And what do I do? Very quickly, I pick up, I think, this one, and I call this D. And if I call this D, then what do? I say that, so this one is, essentially, when I move this to the other side, so this, of course, is an element of V, but since I can move this to the other side, it's also an element of U. Therefore, this is an element of V intersection U, or U intersection V. And to say that that one is an element of V intersection U allows me to cancel these numbers. Have you seen that? You know what I'm talking about? Not quite? Okay. Do you agree that this part, that is an element of U intersection V? No. Okay. Okay. I do like this. I write that this is equal to 0, to the null vector. I call this bit D, and then I rewrite that, that expression in the following way. Alpha 1 T1 plus alpha 2 T2 plus alpha L TL plus beta L plus 1 U L plus 1 plus beta R U R. And this is equal to this other one, but with a minus. Minus gamma L plus 1 V L plus 1 plus, and so on, gamma S Vs. Fine, up to here. And I say that this one is what I'm going to call D. And then I start questioning. where does belong D? And at first I say D sorry, belongs to, so this one allows me to say that D belongs to B. But since it is the same, D also belongs to U, which means that D belongs to U intersection V. Okay? Now, since it belongs to both of them, it means that all this stuff over here, so that also that this one, which is also equal to D, this also belongs to U intersection V. But T1, sorry, T2, TL is a basis of that intersection. Therefore, I can build up any vector by simply combining these ones. Without, I don't need these other vectors over there, which is equivalent to say that beta L plus 1, beta L plus 2, beta R are equal to 0, 0, 0. Do you understand it? Ish. I mean, you need really to devote some time to this, right? Okay, so these are all equal to 0. Okay, and then I keep on writing what I have over there, and I have alpha 1 T1 plus alpha 2 T2 plus alpha L TL, and then I can rewrite here plus gamma L plus 1 V L plus 1 gamma S Vs. And since these were all equal to 0, this is now equal to 0. But now this is what? T1, T2, TL, VL plus 1 Vs is essentially this basis over here. I know that they are linearly independent. Therefore, I know that each of these coefficient is equal to 0. So, are you with me? Ish, more or less? No. Okay. Okay, forget now. Look at this one for the time being. Do you agree with me that this is a basis? Right? We know that if these are vectors over basis, they are linearly independent. Okay? So, if I impose that the linear combination of these vectors is equal to the null vector, what do I get? I get that the coefficient must be equal to 0, 0, 0, because they are linearly independent. Yeah? And that's what I'm doing here. So I say that if this is equal to the null vector, then, and this is equivalent to say that then alpha 1 is equal to 0, alpha 2 is equal to 0, and so on. And they are all equal to 0s. And since all alphas, all betas that I found here, and all gammas are all equal to 0s, then it means that all of them here are linearly independent. Which means that also I have RR plus S minus L vectors that are linearly independent, and they are vectors that belong to S equal to U plus V. So I found these vectors, they are linearly independent, they belong to this set, they are linearly independent, and they span the set. Therefore, what are they? They are a basis. Right? And which means that B, whatever, let's call it just B, composed of T1, T2, TL, UL plus 1, UR, VL plus 1, VS, they are a basis, aren't they? Therefore, the order or the dimension of this set is what? Is the dimension of S, therefore, is R plus S minus L, which is the proof of the theorem. Because this is the dimension of U, this is the dimension of V, and this is the dimension of U intersection. Okay? I mean, you cannot think of coming here and grasp it straight away. You need some time to think for this kind of theorem. Now we use the rest of the time to do something slightly easier, which means we do a couple of exercises. And the first one, can we move this up? I'm going to cancel this. let us make immediately an exercise about the Grassmann formula. And it should be, sorry, I cannot go through everything as I want to. It's okay. Let's go through this one. This. So U is the set of x, y, and z belonging to R3 such that this thing is happening. And V is the set of x, y, and z belonging to R3 such that this other thing is happening. So, for these ones, for these two sets, do the following things. One, find U intersection V. Two, find U plus V. Then try to answer to this question. Is U plus V U direct sum plus V? And fourth is verify the Grassmann formula. Okay? Have you seen exercises like this? You have. I don't know. Do you know how to do it? Yeah? Okay. So, the solution. So, the first question is to find the intersection of the two sets. At first, let us have a look at the first, the sets first. So, if we look at the first set, do you understand what is the geometrical meaning of the first one? No. Okay, that's a plane in space. What about the second one? As well. Okay. Now, to calculate U intersection V means what? It means that I have to take all the points of the first set, which are the points of a plane in the space, and the points of the other plane in space. So, which means that I have x minus y plus 4z equals 0, and then I have y minus z equals 0. And essentially, the intersection is the system of Linear equation, which means the points that are common to both the sets. This is a system of two equations in three variables. So, at first, what is the rank of this system? What's the matrix associated to this? 1 minus 1, 4. 0, 1 minus 1. Are you with me? What's the rank of this matrix? It's 2. The rank is 2. So, I've got three variables. How many solutions do I have?
Infinity to the 1.
Infinity to the power 1. Infinity to the power 1 is what? Is a line in space. It's one dimensional. Okay? What is that line? Now we have to find that line. And essentially, okay, we can use this one because it's the easy one. So y is equal to z, which I'm going to call alpha. And then I replace y and z with alpha. So I have x minus alpha plus 4 alpha equals 0, which leads to x is equal, I hope I'm not making a mistake, minus 3 alpha. Which means that the general solution of the system linear equation is alpha, which multiplies minus 3, 1, 1. What is this minus 3, 1, 1? It's the basis of the system. It's the basis of the vector space, of the vector space intersection. Yeah? So, if you like, VU intersection V has got only one vector, which is V1, or whatever, T1, minus 3, 1, 1, which is only this vector of the space. That one determines the direction of a line, which is my intersection. And this answers to the first question. The second question means that I have to find a basis for U, a basis for V, and then I need to sum them up. Let us find the basis for U, which means, again, U is what? You know, I need to find the points that are, or vectors, x minus y plus 4z equals 0, satisfying this equation. This is, again, if you like, a system of one equation in 3 variables. And in this specific case, if you like, you can think that we have a matrix which is of the type 1, minus 1, minus 4. Right? This is a matrix. Plus 4. Is it? Okay, sorry. What's the rank of this matrix? It's 1. Right? How many variables do I have? 3. How many solutions do I have? I have infinity to the power of 2, which means I have a plane. I have 2 dimensions. Yeah? This is the dimensionality of the problem. I have 2 dimensions, I've got a plane in the space. And how can I find this plane in the space? I am going to call Z alpha, for example, and I'm going then to call Y beta. Why am I picking up 2 parameters? Because here I have a 2, and you know this from last year. Okay? So, I rewrite that as x minus beta plus 4 times alpha, and which equals 0, of course, and which means that x is equal to beta minus 4 alpha, which means that the vector space U is spanned by the following general solution. That is beta minus 4 alpha, comma, we said beta, comma, alpha. Okay? Which now can be rewritten as beta, beta 0 plus minus 4 times alpha 0 alpha, which can be rewritten as beta 1 1 0 plus alpha minus 4 0 1. What does this mean? It means that BU is now made up of 2 vectors, U1 and U2. U1 is this one and U2 is this one. Right? So it's 1 1 0 minus 4 0 1. Okay? What is up? Is this something that you had understood before? Yeah? It's okay. It's nothing difficult. Okay. Fine. Now we have to find the... So can you directly tell me what is the solution of V? Let us say. That's trivia.
Is it delta?
Why delta?
He says well, x, even though there's no x, so you put it as a delta or using the value.
Okay, tell me.
Like so V equals to delta and then lambda lambda.
Delta, lambda, lambda. Okay, this is not wrong at least. But are you sure you understood why you're putting a delta over there? Let me explain you. Essentially, it means that the first component of the vector is 0. So whatever I put here is going to be satisfied. Does it make sense? So it means that, if I write, okay, let me rewrite it this way. Y minus z is equal to 0. So y is equal to z, which means that it is equal, you want to say lambda, but okay, lambda. And that means that, okay, you can look at the things this way. that equation means 0 by x plus 1 which multiplies y minus 1 which multiplies z. That's the meaning of that equation. So whatever I put in x, still is going to be satisfied. Right? So it doesn't matter what is here. So that's the meaning of that. Is this clear? Is this clear from last year or from this year? No, doesn't matter. The important thing is that this is clear now. So the vector space is then going to be V, and this one is the first vector is 1, 0, 0, and the second one is 0, 1, 1. Is that correct? And the sum of this vector space is essentially the sum of all those combinations, and essentially the sum comes up should be R3. Can you see that? No. Yes. Do you see it's R3? Okay. Meaning that if you sum them up, you end up with only 3 parameters. But okay. So the sum is R3. Now the question is this a direct sum or not? No. Why not? Because the intersection, correct, and the intersection is this stuff over here, which is not the root vector, it's another vector. Okay? It's actually infinite points that are all proportional to this one. Therefore, the answer here is no. And let us verify the Grassmann formula. What's the dimension of U?
2.
Correct. How do you do it? It's simpler than what you think. You count, essentially, how do you do it? You pick up V2 and you count them. 1 and 2, there's 2 of them. Yeah? And you write 2. What's the dimension of V?
2.
Okay. What's the dimension of U plus V?
3.
3. What's the dimension of U intersection V?
1.
So, you're right, that 2 plus 2 is actually equal to 3 plus 1. Correct. And that's the Grassmann formula. But I guess you've seen this in a few cases, I want to hope. Yeah? Okay.
But the dimension of U plus V, how did you get 3?
It's R3. Which means that it is any point of the space. Yeah? And actually you can get that. This is V. This is U. So you end up with a bit of calculation. So all the possible, let's say, let's name this U1 and the U2, and let's name this V1 and V2. Now, just not to make the things, if I say like alpha by U1 plus beta U2 plus gamma V1 plus delta V2, what do I get? I mean, what do they span? They span V3. They span R3. Do you see that? Not quite. Okay. What is this vector? This is a vector of the space. This is another vector of the space. When you combine them together, then they are spanning a plane. Do you see that? Okay. And when you add one more vector here, they essentially are spanning the space, and one more is redundant. Okay? Or if you prefer, out of these 4 vectors, 3 of them are linearly independent. And if 3 of them are linearly independent, then it means that that they are spanning the space. Okay? Okay. Now, let's go to the next. Okay? Are you able to check the linear independence of the 4 vectors?
Yeah.
Yeah. From last year. Okay. Is everybody able to check the linear independence? Do you remember how to do it? Yeah? Well, if you don't, please be right. Okay? And now I'm going to ask you a a couple more things. Let's do an easy one first, just so that we can rest a bit. And then the other one we just started because we don't have that. Okay, the next is something which we have seen so many times. If I write R22, whatever, R33, R33, the set of all the square matrices of order 3, and I indicate with dot the product of matrices. Do you remember? Is that an algebraic structure? Yes, why is it? We've seen it so many times. Is it?
Internal composition. Internal.
So I pick up two square matrices, I multiply, I get the square matrix. Okay, that means internal composition. Second bit, is this a monoid? Why?
Because
Commuted.
which is the identity matrix.
Ah, okay, that's the
Yeah.
That's semi-group.
Yeah.
okay. It's a semi-group, yes, because this is associated. Is it a monoid?
Yeah, because the identity matrix is inverse.
Not quite. It's the neutral element.
So neutral.
Careful. And is this a group?
No,
Why not?
two operator. It's got the one operator. You need two operator.
No, definitely not. That's not the point.
If he has the interest.
What?
Singular matrix.
What's else? So is this a group? Yes or no?
Similar to singles.
Okay. What do I need to have a group? I need that all the elements should be invertible. Are all the elements invertible? No. Because some of these elements are invertible when the matrices are non-singular, while some others are non-invertible if the matrix is singular. Therefore, this is not a group. Okay? We have seen this a few times. It's written on the notes. I mean, you need to spend a bit of time revising. And now we look at this last one. Yeah, because we really don't have time. I just started, but I have already solved for you, and I've already recorded. And I'm just checking. We consider Z, okay? And we consider A and B elements of Z. We introduce the following operator, A plus B minus AB. Verify whether or not this is associative, and verify whether or not this is a monoid. Well, whether or not it's a monoid, and verify whether or not this is a group. Do you remember me doing this? Okay? Do you remember what the answer was? I don't have time to go through all of it. Or what was the point in this exercise? Do you have any? I mean, it's of course it's on the book, on the notes that you have. I have done it. There is a video about this. I mean, I don't know what else I can do for you. I mean, you must give the right answer now. Anyway, the right answer is yes. It is. You can prove associativity. Therefore, that one is a semigroup. And yes, you can find a neutral element, and which is a monoid. Do you have any clue how to find whether or not this is a monoid? What was I doing in that case?
Is it the neutral element?
It's a neutral element. What do I do in order to find a neutral element?
Should equal to 0?
No, not quite. That's the answer. But how did I do that?
Is it if it's opposite?
Let's say I want to do this by the. Let's say I want to find this one, and I want that this gives me this. That's how I start. Yeah. And then I do not put, instead of B, I put E, and I impose that one, and then I find what I find that essentially E is equal to 0. Is that correct? Because if I put 0 here, then I have A plus 0 minus 0, it's A, so it's correct. That's the inverse element. And so, considering that E is equal to 0, now I have to check whether or not this is a group. What do I have to do?
Check for inverse.
Check if all of them are invertible. And I have to say what are the invertibility conditions. What means invertibility condition? It means that I do A star A minus 1 equal to E, which is 0. Which means A plus A minus 1 minus A minus 1, which is not equal to 1 as such. No, actually it is in this case, yes. Which means A plus A minus 1 minus 1 equal 0. Then I, is that correct?
Yeah.
Yeah? Then this leads to say that A minus 1 is equal to 1 minus A, but I should have 1 over. No, that's, sorry, what am I doing? Sorry. Sorry. I want to do it. And this one now is A minus 1 minus A minus 1 is equal to minus A, and now this makes more sense. And A minus 1, which multiplies 1 minus A, is equal to minus A, and this should mean that A minus 1 is equal to A, which divides by A minus 1. Okay? So this is the inverse element. And now this makes sense. Sorry about before. Now, if this is the inverse element, is this a group or not?
Yeah.
No. When I mean, this is the inverse element, and
Like for all elements.
does this mean that every element is invertible?
No.
No. Which are the elements that are invertible? Only 2, for example. 2 is invertible because 2 divided by 2 minus 1 is 1, and so we have that A is equal to 2. If A is equal to 2, A minus 1 is equal to 2. Correct? But if A is equal to 0, of course, because it's the neutral element, A minus 1 is equal to 0. But if, for example, A is equal to 1, well, then it's a good example. If A is equal to 3, for example, I have that A minus 1 is equal to 3 divided by 2. So essentially, I do not have all of them that are equal. Okay? Does it make sense?
Yeah.
Yes, it does. Okay, fine. I hope I have not told you anything silly. Yeah, must be 0, 2. Yeah, that's a. So essentially, okay, let me rephrase this way. In order to be invertible, I need that this thing is verified. In all the other cases, which means this one and this one, right? I thought I had a green one. So the answer is only these 2 elements are invertible, all the others are not invertible, therefore this is not a group. Is the message clear that this is the right answer? Okay? Fine. So that one is not a group because only 2 elements are invertible, all the others are not.